February 19th, 1942. Buna Airfield, Papua New Guinea. Lieutenant Thomas Lynch crouches beside the intact A6M Zero fighter, his hands trembling as he pries open the inspection panel on the fuselage. The aircraft sits abandoned on the jungle strip, its distinctive low-wing configuration and sleek lines still menacing despite being motionless. The morning heat already presses down like a weight, but Lynch barely notices. He's found something impossible. The aluminum skin beneath his fingers feels wrong, too thin. He pulls a pocket knife and tests the thickness. 2 millimeters, perhaps less. This cannot be right. No military aircraft uses skin this thin for primary structure. His knife penetrates the metal with almost no resistance. He moves to the wing root, finding the same impossibly thin construction. The fuel tanks visible through the access panel show no protective coating, no self-sealing compound, no armor plating, just bare aluminum holding aviation fuel. Lynch, an intelligence officer with the 5th Air Force, has examined dozens of aircraft. He knows what fighters should look like inside. American P-40s feature armored windscreens, protected fuel tanks, redundant systems. Even the outdated P-36 has basic protection. But this Zero, Japan's premier fighter, the aircraft that has dominated Pacific skies for 2 months, has nothing. No armor behind the pilot's seat, no protected fuel lines, no fire suppression system beyond a basic extinguisher. He calculates quickly. The weight saved must exceed 200 kilograms. That's the weight of a full-sized man. The Japanese have removed everything that might keep a pilot alive and converted that weight directly into performance. Every kilogram of protection has been sacrificed for speed, range, and maneuverability. Lynch photographs the exposed systems methodically, knowing that what he's documenting will revolutionize American tactical doctrine. Every assumption about why the Zero dominates, about what price Japanese engineers were willing to pay for that dominance, is about to be rewritten. This aircraft isn't just unprotected. It's deliberately, systematically, ruthlessly optimized to kill its own pilot the moment it takes battle damage. The Zero's reputation was forged on December 7th, 1941. That morning, 189 Japanese aircraft struck Pearl Harbor in the first wave. Among them, 43 A6M Zero fighters provided escort and ground attack capability. The Zeros flew from carriers 230 miles north of Oahu, a distance that American carrier fighters couldn't match. During the attack, not a single Zero was lost to enemy action. The performance shocked American observers who witnessed the attack. The Zeros demonstrated climb rates exceeding any American fighter in service. They executed maneuvers that American pilots considered impossible for carrier-based aircraft. Their range permitted operations far beyond what American doctrine assumed possible for fighters. The few American pilots who managed to engage Zeros during the attack found themselves outmatched in every parameter except diving speed. 3 days later, December 10th, 1941, Zeros demonstrated their capability against contemporary British fighters. Over Malaya, 27 Zeros from the 3rd Air Group encountered British Buffalo and Hurricane fighters defending against Japanese bomber formations. In the engagement that followed, Japanese pilots claimed 11 Allied fighters destroyed. 0 losses, 0. The pattern would repeat throughout December 1941 and into early 1942. By January 1942, Allied intelligence had compiled disturbing statistics. In engagements across the Pacific and Southeast Asia, Zeros consistently achieved kill ratios exceeding 10-1. Over the Philippines, American P-40 and P-35 fighters suffered devastating losses in every encounter. Over Java, Dutch Brewster Buffaloes proved helpless against Zero formations. Over Burma, British Hurricanes, aircraft that had won the Battle of Britain, were systematically destroyed by Japanese fighters that seemed to operate by different physical laws. The Zero's specifications explained its dominance. Maximum speed of 533 kilometers per hour, service ceiling of 10,000 meters, range of 3,104 kilometers with external tanks exceeding 1,900 miles. Rate of climb, 15.7 meters per second. Wing loading of just 107 kilograms per square meter lower than any fighter in Allied service. Empty weight, 1,680 kilograms, remarkably light for a carrier fighter. The armament complemented this performance. Two 20mm Type 99 cannons in the wings provided devastating hitting power. Two 7.7mm machine guns in the nose offered high rate of fire for ranging and incendiary work. The combination gave Zero pilots the ability to destroy enemy aircraft with short bursts while maintaining ammunition for extended combat. Lieutenant Saburo Sakai, who would become Japan's most successful surviving ace, described the Zero's capabilities in his combat memoir. The aircraft responded to controls like no fighter I had flown. It could outturn anything the enemy possessed. It could outclimb their fighters at any altitude. Range permitted us to escort bombers to targets the enemy thought were beyond fighter escort distance. We owned the sky. By March 1942, the Zero's reputation had achieved mythological status among Allied forces. Pilots reported that Zeros could turn inside any Allied fighter, climb faster than any Allied aircraft, and operate at ranges thought impossible for single-engine fighters. Intelligence reports described the Zero as potentially invincible in dogfighting, cautioning pilots to avoid engagement unless holding overwhelming numerical or positional advantage. The shift began subtly in April 1942, then accelerated through the summer. American pilots, forced to develop new tactics through brutal trial and error, discovered that the Zero's dominance had boundaries. The first major engagement revealing Zero vulnerabilities occurred on June 4, 1942, during the Battle of Midway. American dive bombers attacking Japanese carriers received fighter escort from F-4F Wildcats, aircraft inferior to the Zero in almost every performance metric except one, structural strength. Wildcat pilots trained in new boom and zoom tactics, developed by Lieutenant Commander John Thack, avoided turning engagements entirely. The new American doctrine exploited the single advantage Wildcats possessed: diving speed. Wildcats could dive faster than Zeros and could withstand higher G-forces during high-speed maneuvers. American pilots would dive on Zero formations from altitude, fire a burst, then extend away in a high-speed dive the Zero couldn't match. If a Zero pursued into the dive, its lighter structure prevented it from following through high G pullouts. More importantly, American pilots discovered the Zero's catastrophic vulnerability to battle damage. Lieutenant Commander James Flatley reported after an engagement in May 1942, "We hit a Zero with a single burst from our .50 calibers. The aircraft exploded instantly. No fire, no smoke trail, just an explosion. We thought we'd hit ammunition or fuel with a tracer. Then it happened again and again. Every Zero we hit exploded." The pattern repeated with disturbing consistency throughout June and July 1942. Combat reports from Guadalcanal, New Guinea, and the Aleutians described identical observations. Zeros hit anywhere in the fuselage or wings burst into flames immediately. Incendiary rounds ignited fuel with near certainty. Even non-incendiary rounds produced catastrophic results if they struck fuel tanks or lines. By August 1942, Zeros had acquired grim nicknames among American squadrons. Flying lighter became common. One-shot Zero referred to the aircraft's tendency to explode from single hits. Flying Molotov referenced the firebomb-like combustion when fuel ignited. Lieutenant Commander John Thack, whose Thack-Weave defensive tactic would become standard doctrine, summarized the tactical shift. "We learned that we didn't need to dogfight them. We couldn't dogfight them, but we didn't need to. Hit them once and they burned. The trick was getting that one hit, then getting away before their maneuverability brought guns on you." The kill ratios shifted dramatically. In early 1942, Zeros achieved 10-to-1 or better exchange rates. By late 1942, the ratio had reversed in many engagements. American pilots, flying aircraft with protected fuel tanks and armored cockpits, survived battle damage that would have been instantly fatal in Zeros. Japanese pilots, flying unprotected fighters, died from wounds and fires that American pilots would have survived. The captured Zero at Buna provided the first complete technical analysis of Japan's premier fighter. Lieutenant Lynch's initial examination in February 1942 was followed by comprehensive evaluation conducted by the Allied Technical Air Intelligence Unit throughout March and April. Engineers removed panels systematically, documenting every system. The fuselage skin measured 1.5 to 2.0 millimeters throughout most of the structure, approximately 30% thinner than comparable American fighters. The wing skins ranged from 1.0 to 1.5 millimeters. American engineers calculated that this thin construction saved approximately 180 kilograms compared to standard American practice. The fuel system revealed the Zero's fundamental vulnerability. 3 fuel tanks, one in each wing root and one behind the pilot, contained a total of 518 liters. None featured self-sealing compounds. None had protective armor. The tanks consisted of thin aluminum with basic baffling to prevent fuel surge. Fuel lines running through the fuselage and wings had no protective sheathing. American engineers tested the fuel tank construction by simulating combat damage. A single .30 caliber round punctured the tank and created an opening approximately 8 millimeters in diameter. Fuel poured from the hole at a rate exceeding 1 liter per minute. In combat conditions, with the aircraft maneuvering and fuel sloshing, leakage would be even more severe. If a tracer or incendiary round struck the tank, ignition was virtually guaranteed. The cockpit armor, or rather its absence, shocked American evaluators accustomed to protected crew stations. The pilot's seat had no armor backing. The instrument panel had no protective plating. The windscreen used standard glass with no armored layer. A 7.7 millimeter round could penetrate the seat back and kill the pilot. A 12.7 millimeter round could penetrate the windscreen from any angle. Structural testing revealed why Zeros couldn't follow Wildcats into high-speed dives. The wing structure, optimized for lightweight and low wing loading, showed stress damage at speeds exceeding 600 kilometers per hour. The thin skin buckled under high G-forces. American engineers calculated that the Zero's maximum dive speed was approximately 630 kilometers per hour before structural failure became likely. The Wildcat could safely dive to 805 kilometers per hour. The weight savings were precisely calculable. Self-sealing fuel tanks would have added 45 kilograms. Pilot armor would have added 55 kilograms. Cockpit protection would have added 30 kilograms. Structural reinforcement to permit high-speed diving would have added 70 kilograms. Total protection systems deleted 200 kilograms. That 200 kilograms translated directly into the Zero's performance advantages. The light wing loading of 107 kilograms per square meter enabled the tight turning radius. The low empty weight of 1,680 kilograms enabled the exceptional climb rate. The weight savings permitted fuel capacity that gave the Zero its extraordinary range. American engineers concluded that the Zero represented a coherent design philosophy. Maximize performance by eliminating all protection. The aircraft achieved its capabilities not despite its vulnerabilities, but because of them. Every kilogram of armor deleted became a kilogram available for fuel or performance. The Zero's designers had made a calculated trade: pilot survival for tactical superiority. The comparison with American practice was stark. The F-4F Wildcat, the Zero's primary opponent in 1942, featured comprehensive protection. Armor plate behind the pilot's seat, 9.5 millimeters thick. Armored windscreen, 38 millimeter laminated glass and armor. Self-sealing fuel tanks, standard across all 6 tanks, totaling 583 liters. The protection systems added 193 kilograms to the Wildcat's empty weight. That weight penalty cost the Wildcat dearly in performance. Maximum speed, 512 kilometers per hour, 21 kilometers per hour slower than the Zero. Climb rate, 12.1 meters per second, 23% slower than the Zero. Turn radius, significantly worse at all speeds. Range, 1,337 kilometers, less than half the Zero's range with external tanks. But the protection systems meant that Wildcats returned from missions that would have been fatal in Zeros. Pilots survived wounds that would have killed Zero pilots. Aircraft absorbed battle damage that would have destroyed Zeros. The survival statistics told the story. Wildcat pilots who took battle damage had a 60% probability of returning to base. Zero pilots who took comparable damage had less than 15% probability of survival. The requirements that created the Zero were issued in October 1937 by the Imperial Japanese Navy. The specifications demanded performance that no existing fighter could achieve. Maximum speed of 500 kilometers per hour, climb to 3,000 meters in 3.5 minutes, range exceeding 2,000 kilometers with external tanks, and maneuverability superior to all contemporary fighters. The Navy also specified armament unprecedented for carrier fighters, 2 20mm cannons, plus 2 machine guns. The combination of speed, range, climb, maneuverability, and heavy armament created an engineering problem that appeared unsolvable. Every calculation showed that meeting all requirements simultaneously was impossible with available technology and materials. Mitsubishi assigned the project to Jiro Horikoshi, a 34-year-old engineer who had designed the previous generation A5M fighter. Horikoshi understood immediately that conventional design approaches couldn't satisfy the Navy's demands. The weight budget permitted no compromises. Every gram had to be justified and optimized. Horikoshi assembled a team of engineers at Mitsubishi's Nagoya facility and began systematic weight reduction analysis. They examined every component, every system, every structural element. Where could weight be reduced without compromising flight performance? What systems were truly essential? What protection could be eliminated? The calculations were brutally clear. The Navy's requirements demanded a maximum weight of 2,400 kilograms fully loaded. The engine, propeller, and fuel for the required range consumed 1,200 kilograms. The armament and ammunition added 220 kilograms. The airframe structure, landing gear, and flight controls required approximately 780 kilograms minimum. That left exactly 0 kilograms for protection systems. Horikoshi's team faced a binary choice: meet the Navy's performance requirements with 0 protection, or add protection and fail to meet requirements. There was no middle ground. The mathematics permitted no compromise. Every kilogram of armor meant either reduced range, reduced armament, or reduced performance. All three were unacceptable to the Navy. The team made their decision in early 1938. Protection systems would be eliminated entirely. Fuel tanks would be unprotected aluminum. The pilot would have no armor. The aircraft would use the thinnest skin, consistent with structural integrity. Every possible weight reduction would be implemented regardless of impact on survivability. Horikoshi understood the implications. In a letter to a colleague dated March 1938, he wrote, "We are building a fighter that can achieve everything the Navy demands, but the pilot who flies it must understand that he cannot be hit, not once. Any battle damage will likely be fatal. We are trading absolute performance for absolute vulnerability." The first A6M prototype flew on April 1st, 1939. The aircraft exceeded every performance specification. Speed topped 509 kilometers per hour. Climb rate surpassed requirements by 15%. Range with external tanks reached 2,200 kilometers. Maneuverability exceeded the previous generation fighter by wide margins. The Navy accepted the aircraft immediately, designating it the Type 0 carrier fighter, 0 for the Japanese, year 2600, 1940. Production began in July 1940 with initial deliveries to frontline units in August. By December 1941, approximately 420 Zeros were in service. The design philosophy reflected broader Japanese military culture. The Bushido code emphasized courage, sacrifice, and acceptance of death in service. Japanese doctrine assumed that superior training, skill, and fighting spirit would provide adequate protection. Physical armor was unnecessary for warriors who embraced death as part of their duty. This philosophy worked perfectly when Japanese pilots held qualitative advantages in training and experience. The first generation of Zero pilots averaged 500 to 800 flight hours before entering combat. They were the elite of Japanese naval aviation, capable of exploiting the Zero's performance to maximum effect while minimizing exposure to enemy fire through superior tactics and skill. But the philosophy collapsed when attrition destroyed this elite cadre. By late 1943, replacement pilots averaged 100 to 200 flight hours of training. They lacked the skill to avoid damage through maneuvering alone. The Zero's lack of protection, manageable for elite pilots who rarely took hits, became a death sentence for average pilots who regularly sustained battle damage. By 1945, the Zero had transformed from the Pacific's most feared fighter into what American pilots called easy meat. Total production reached 10,939 aircraft across all variants. Fewer than 200 survived to war's end. The rest were destroyed in combat or lost to accidents, many resulting in post-crash fires that unprotected fuel systems made inevitable. Pilot casualties were catastrophic. Conservative estimates suggest over 5,000 Japanese pilots died flying Zeros. The majority died not from direct hits, but from fires and explosions caused by fuel tank damage that would have been survivable in protected aircraft. Lieutenant Commander Saburo Sakai, one of Japan's top aces who survived the war, wrote, "The Zero was a magnificent fighter that asked us to die for its performance. Every mission, we knew that a single hit could kill us. Most of my friends died burning in their cockpits, not from enemy bullets, but from fires the Zero's design made inevitable." Combat statistics from 1944 illustrated the difference. American pilots who took battle damage had a 70% survival rate. Japanese pilots in Zeros who took comparable damage had a 20% survival rate. The Zero achieved everything its designers intended: unmatched maneuverability, exceptional range, devastating firepower. But these capabilities meant nothing when pilots died at unsustainable rates. American designers accepted lower performance to ensure survivability. They built heavier fighters that couldn't match the Zero's agility, but brought pilots home. The unprotected fuel tanks weren't a design failure. They were a design choice. Japanese engineers built exactly what their requirements demanded. Those requirements simply didn't include bringing pilots home alive. And in that decision lies why Japan's most successful fighter ultimately failed. Because warfare is sustained attrition, and attrition destroys forces that cannot protect their most valuable asset: trained pilots who survive to fight again. If you found this story fascinating, smash that like button and subscribe for more untold stories from aviation history. Share this with any history buffs you know, and drop a comment. Did the Zero's designers make the right choice, or was the cost too high? Thanks for watching, and I'll see you in the next one.